Hello, my name is Liam Alcox, and my project is on magnetism, specifically the study of ferromagnetic properties. Magnetism is a property that results in macroscopic attraction of materials based on their atomic structure. Magnetic fields are produced by the motion of a charge in space. On the atomic level, magnetic forces arise due to the motion of electrons in an atomic orbital. This motion leads to the creation of a magnetic dipole moment associated with the atom. The subatomic particles that make up each atom have an intrinsic spin associated with their motion that creates a magnetic dipole moment as well. Both moments contribute to the magnetic field associated with the atom. These atomic level magnetic fields are what give rise to the macroscopic property of magnetism that is seen within various materials. In a way, all materials exhibit some sort of magnetic property. However, there are specific categories that represent materials for which this property is macroscopically visible, whether it is induced or inherent magnetism. In this presentation, I will focus on one specific category of materials which show a high level of magnetism, ferromagnetic materials. The most common types of ferromagnetic materials include iron, nickel, and cobalt. Within the grains of a ferromagnetic crystalline solid, a significant amount of the atoms have associated magnetic dipole moments and act as atomic electromagnets. Within these grains, the atoms align themselves parallel to one another to reinforce the magnetic field. However, because this net magnetic field is randomly oriented within each grain and therefore will not result in inherent macroscopic magnetism, it is not naturally magnetic as we perceive it. However, once an external magnetic field is applied to the material, the net magnetic dipole moment within each grain will align with the external field, increasing the magnitude of the magnetic field that would be present despite the ferromagnetic material. Here we see a visual representation of this. As you can see, naturally all fields will be randomly oriented, and that's displayed on the left. However, within each grain, the fields are parallel and uniform, again displayed on the left. Displayed on the right is what happens when the crystalline solid is exposed to a induced magnetic field. Many factors can affect the strength of the induced magnetic field within a ferromagnetic material. I will explore these factors in relation to iron. Three major factors include temperature, applied force, and impurities. Because an increase in temperature of a crystalline solid increases the kinetic energy, vibrational energy of its atoms at higher temperatures, the magnetic dipole moments within each grain become highly random and misaligned due to an overall increase in entropy. The temperature at which iron loses its magnetic properties is known as the Curie temperature, which is 770 degrees Celsius. Randomization of the magnetic dipole moments can also result from a rapid application of force, i.e., dropping the ferromagnet. This can temporarily misalign the magnetic dipole moments, but the reapplication of an induced magnetic field will realign said moments. Ferromagnets also remain magnetic after application of an induced magnetic field. However, the magnitude is lower than if it was in the presence of an external magnetic field. The final factor is what is being studied today, impurities. Here you can see the cell of pure alpha iron on the left versus the unit cell of impure alpha iron, basically steel, on the right. As you can see in the unit cell of steel, there are carbon atoms as well as other interstitial atoms. In the unit cell of steel, the black atoms represent possible tetrahedral interstitial impurities, and the red atoms represent possible octahedral interstitial impurities. Carbon can be at any one of these points at any point in time, and it is also constantly moving. Magnetism is affected by impurities for a few reasons. The first is that carbon is a diamagnetic, and the net magnetic dipole of the atom will directly oppose the field induced upon it. Second, addition of carbon results in iron carbide precipitates, which lends an increase in density and decrease in permeability. Third, iron carbide precipitates result in an ion of iron that has a weaker magnetic dipole moment than the bulk of the ions present in the pure iron. Having said this, although impurities do negatively affect the magnetism of steel, however, the addition of carbon increases the magnetic coercivity of the solid. This means that steel with a moderate carbon content will take longer to magnetize, but can be converted into a permanent magnet once a significant magnetic field is applied. Soft iron, high purity iron, does not retain its magnetism as it both magnetizes and demagnetizes very quickly and with little applied magnetic field. I performed an experiment in which I explored how impurities affect the force induced by magnetism on iron. I compared carbon steel 1144, carbon steel, and high purity iron. And this is a summary of that experiment. The materials for my experiment include a magnum with a maximum capacity of 16 pounds, depending on its material, high purity soft iron, and carbon steel, 1144 carbon steel, which means that there is some sulfur as well as carbon present within the iron. In this experiment, I was attempting to determine which material exerts a higher force as a result of the induced magnetic field. To measure the force, I secured the magnet to a bucket before attaching it to the steel rod and high purity iron rods. I first tested the bucket empty, then continued to lift the bucket as water was being added in 100 milliliter integers. I found that the bucket pulled the magnet off at a lower weight for the steel than it did the iron. This trend, as well as the difference in the weight of the bucket at detachment, remained largely constant in the 2 repetitions, with the difference in weight being an average of 0.2 kilograms, making the difference in force about 1.9 newtons. It can safely be assumed that the magnitude of the magnetic field in the high purity iron is larger than that of the steel. The minor difference is likely due to the relatively low amounts of impurities in the 1144 steel. In industry, ferromagnetics are highly useful as they allow for a magnet that can be turned off and on, as well as a magnet whose field can change signs. Ferromagnets are regularly used in electric motors, golf carts, for example. They are also, more importantly, used in transformers, which are essential in the transport of energy via power lines to our infrastructure. Ferromagnetic material also plays a large role in our current digital age, as hard drives um, use ferromagnetic materials to assist in the process of encoding bits of data. Without these materials, many of our electronics would not be possible. Thank you for listening, and are there any questions?